To finish our introduction to integration by parts, I want to look at two different topics. One of them is integrals of the type an exponential function multiplied by a sine or cosine function. The second one is called the tabular method. It's a method by which, under certain circumstances, you can do repeated integration by parts in a very efficient and quick manner. As an example of the first topic, let's think about the integral of e to the 2x times cosine 3x with respect to x. We'll try integration by parts with the u being e to the 2x and the dv being the rest of it. If u is e to the 2x, then du dx is 2e to the 2x, and du is 2e to the 2x dx. dv dx will be cosine 3x. V must be an antiderivative, which would be 1/3 sine 3x. Writing out the integration by parts formula, the integral of u dv will be uv minus integral of v du, all of which we now know. Collecting terms and pulling constants out of integrals, we get this result. At first glance, it looks like this is no better than what we started with, because we still have an integral involving exponential functions and trig functions, except now it's sine of 3x instead of cosine 3x. So I'll think of going off and calculating the integral of e to the 2x sine 3x in some way, and then inserting the result inside the square brackets and simplifying. A key point is, in this kind of integral, if I let the u be the exponential function on the first go-round, then I should do that again on the second go-round. So I'm going to let u equal e to the 2x. I'm going to let dv be sine of 3x dx. du again is 2e to the 2x dx. The v is negative 1/3 cosine 3x, and then I can write the integration by parts formula down again. The quantity inside the square brackets is negative 1/3 e to the 2x cosine 3x plus 2/3 times the integral of e to the 2x cosine 3x dx. Putting all of this together, we have the following atrocious looking mess in which the integral of e to the 2x cosine 3x shows up on both sides of the equation, but we're going to do something that's very similar to what we've done in the past. After writing out all the distributive law and multiplications by 2/3, we see that if we add 4/9 times the integral that we're after, it'll all move over to the left-hand side. 1 plus 4/9 is 9/9 plus 4/9, which is 13/9. Finally, if we multiply through by 9 and divide through by 13, we will finally know an antiderivative of e to the 2x cosine 3x with respect to x, which then we'll add a constant of integration to, and to know all of the antiderivatives. Lastly, I want to introduce what's called the tabular method. This method works especially well if you have a problem in which you're integrating a product of two things, one of which is a polynomial and the other one of which is easy to integrate over and over again. As my example, I'm going to use the integral of 2x squared plus 5x plus 1 multiplied by e to the x. I'm going to let u be 2x squared plus 5x plus 1, so that du is 4x plus 5 dx. I'll let dv be third e to the 3x dx. Write out the integration by parts formula, being careful to keep separated the things that originated from the polynomial and the things that originated from the exponential. Writing out this integration by parts, we get kind of a messy thing. I've put it inside of brackets in that second term to keep things straight. I'm going to have 2x squared plus 5x plus 1 times 1/3 e to the 3x minus the quantity 4x plus 5 times 1/9 e to the 3x minus minus is plus 4 times 1/27 e to the 3x is what I get when I integrate 1/9 e to the 3x. I'm going to write down the polynomial, and I'm going to write down the e to the 3x. What I'll do is I'll take derivatives of the polynomial one after the other until they all start coming up 0. So 2x squared plus 5x plus 1, the derivative is 4x plus 5. The derivative of that is the constant 4, and all further derivatives are 0. Integrating, not differentiating, the other quantity, I get 1/3 e to the 3x, 1/9 e to the 3x, and 1/27 e to the 3x. If you connect numbers in the first column with numbers in the second column, which are one unit down, you'll notice that the factors that you get are 2x squared plus 5x plus 1 multiplied by 1/3 e to the 3x. Also, you'll have 4x plus 5 multiplied by the quantity 1/9 e to the 3x. And you'll have the quantity 4 multiplied by 1/27 e to the 3x. Looking at what came out of integration by parts, these are the individual terms. You add the first product, you subtract the second one, then add the third one. If you had more terms, you would continue alternating adding and subtracting. This comes from the minus signs in the integration by parts formula. As additional example of this, let's look at the integral of x squared plus 8x plus 2 e to the x with respect to x. As before, write the polynomial, x squared plus 8x plus 2. Write the other factor, e to the x. The derivative of x squared plus 8x plus 2 is 2x plus 8. The derivative of 2x plus 8 is 2, and all further derivatives are 0. Link the pairs of numbers by the downward sloping lines, and then add and subtract alternately. You get x squared plus 6x minus 4 e to the x plus a constant. If you check that by taking the derivative, you find out that you get what you're supposed to get. This is about everything I want to say about integration by parts. Hopefully it's clear enough. I hope that everyone's having a good day, and I'll talk to you again soon.